All right, so yesterday we had our activity where we took the tuning forks and we struck the tuning forks and they vibrated back and forth. Same deal right now, I am talking and those two vocal cords are vibrating back and forth and I'm able to produce what? Sound. Do you remember what we called that yesterday? It started with an R, resonance. Then I also used the actual PVC tube in order to amplify that sound. And like I had said, you were listening for that spike where it went the woo woo type sound, which hopefully you guys heard it yesterday. As long as you spread out enough throughout the hall and in here, you should have heard that a little bit. All right, reflection. So once you guys move on and you go into your junior and senior year and you're taking physics, you guys will focus more so on the math in terms of reflection. So obviously reflection can be a variety of things. It can be reflecting light. So I can take this, shine it on there, but oh man, that's not a reflective surface. Because otherwise if it was, who would I hit? I'm thinking Hadley. I might be able to hit Hadley if this was to reflect over there, right? But it's not reflecting, right? If I had a reflective surface and I shine it straight on, it would come back exactly that exact same position. Just like a wave, if I shout in the Grand Canyon and I say, hello, what am I going to hear? Hello, 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 right? It's going to echo, it's going to bounce off those walls. So it doesn't necessarily matter whether it's actual light that's going to strike that reflective surface or if it's sound, both are going to be able to have it bounce off the surface. So a reflection is when it bounces off, okay? When you get into physics, you're going to focus a little bit more on the angle of which it strikes. If it strikes with 20 degrees, it's going to bounce off at 20 degrees, okay? So the angle of incidence is equal to the angle of reflection. That's where you're going to eventually get to if you continue on the path of physics, okay? So in order for reflection, with reflection, the wave bounces off, okay? That's the big takeaway with this one. Some technology that we utilize with reflection is sonar. So boats sending out actual sound, it's going to go down. Once it hits an object, that is going to bounce back and come back. So if we know the speed of sound, and we know how long it took for it to go down and back, can I figure out how far it is? Yeah, the speed is distance divided by time. We can calculate speed of sound. We calculated speed of sound yesterday, which was how much? 340 is what we were shooting for, right? So about 340. So the speed in water is a little bit different. It's not 340, it's a little bit faster. So we could go ahead and calculate that. Boop, have it come on back, figure out where it is. Looking for sunken ships. Trying to detect if there's any enemy submarines, trying to find schools of fish. We can use sonar for a lot of different things. We can also use here, any other guesses? What other animals use sonar? Bats, right? So main one that you guys probably are going to think of, the echolocation, right? So using echolocation to determine hey, is that a tree I'm going to run into? And how close am I to that tree? So then I can fly away from it, okay? So that actually bounces back. We also use reflection a lot in terms of GPS. If you are using GPS, you're going to send out a wave. It's going to go up to the satellite, and it's going to ping, and it's going to come back down. And it's going to keep updating as you move, right? So that's another way that we can actually use reflection. Refraction. This is when the wave actually gets bent. So if you guys put a straw in a cup of water or you put a pencil in a cup of water, it looks like it's bent, right? Or it's broken, right? When really it's not, okay? That's because the light was in a gas up above the pencil and now the light is down in the water. So when it enters different mediums, do you see how the angle changes? And so again, if you end up going on, you'll solve for what is that angle? What's the angle here? It's called the N value. What is the substance end value for substance 1 and 2. That's going to dictate whether it bends towards the perpendicular or away from the perpendicular here. Okay? But main thing I need you guys to know, refraction is the bending of waves as they go into different mediums. If I shine light through a prism, do you see how the light looks like it should keep going like this? But it bent when it went into the prism, and then look, it's going to bend again as it comes out of the prism. So anytime light passes into a different medium, it's going to bend. It's going to bend. All right, questions on reflection or refraction for right now. So which one bounces back? Reflection. Which one gets bent? Refraction. Have you guys ever, I'm going to take you guys back to when you were a little kid and you were in the pool and you were playing ring toss, or you were playing save the fishies at the bottom of the ocean, or whatever you were actually playing in the pool. You know how it looked like it's right here, but when you take your hand and you try to grab it, it's not actually right there. It's a little bit off from that position. That's because of this, right? If you ever look at, like, I always think it's cool when you look at your hand under the water, like where it actually is versus what it looks like where it is with your eyesight. So that's all refraction. That happens because the light is going through a different medium, okay? So it actually gets a little bit bent. Interference is our next one. So this is number 3. Interference can either be constructive, where it makes a bigger wave or a louder sound, or it can be destructive when the sound gets quieter or if it cancels it out entirely. Why would I want to cancel something out? Can anybody think of what my wave technology is for canceling it out? Noise canceling headphones, right? So I'm going to jump ahead a little bit. Noise canceling headphones, right? So noise canceling headphones, you don't want to hear me lecturing if you want to just be listening to your own music, right? If you are riding on the subway and you have your headphones on, you don't want to hear all the other external noises. You just want to hear your music. So noise canceling headphones, think about if you're ever in a studio. So if you're in a studio and you're singing, and in the one studio you got a screamo band, and then in the other studio you have somebody singing a lullaby. Do you want those two kind of leaching into each other? No. So what do we put on the walls in like recording studios? Yeah, soft materials, foam. They also make them look kind of wavy. If you've ever been to COSI, have you guys ever been to COSI? They have that room where you can literally stand there and you can scream and it disappears. Sound goes away, right? So that comes back to interference. Now, if we are looking at a wave diagram, so if you look here, when you're trying to determine is it constructive or destructive, anytime that these are on the same path, so do you see how these two waves are coming on the same path? They're both going up, both going down together, both coming up, both going down together. Do you think that's going to be constructive or destructive? Constructive. They're going to go together. Whereas on this next one, do you see here how this is still above rest and this is now below rest? So those are opposite. So when they're opposite of each other, they're going to end up canceling each other out. If they have the exact same amplitude, they'll cancel out 100%, or it'll just end up generating a smaller wave. And so that smaller wave, it might cancel out completely, or it just might be quieter, whichever it may possibly be, but that would be interference, okay? So biggest one are those noise canceling headphones that you guys all love so much. Did you guys used to have, we talked about this first period, did you ever have skull candies? Do you guys remember skull candies? That was, I don't know how many years ago. Those ones were huge. Before, like, obviously all the AirPods and stuff like that. Those were like the primo noise canceling headphones. All right, next up, number 4, Doppler effect. When an ambulance comes close to you, what do you hear? Yes, you hear the siren. You are right. Yes. Does it sound the same the entire time, though? No. Yeah, when it gets closer to you, it sounds really loud, and doesn't it kind of hurt your ear? Because it has a higher Frequency, right? Remember I told you higher frequencies do what to my ear? Hertz, right? So then as it moves away from me then, it doesn't sound as loud. The frequency seems to have gone down. Now the real kicker is though, it's the ambulance producing that siren, right? Did the siren actually change frequencies and change its sound? No. So this is when we look at Doppler effect. Doppler effect is kind of a weird one because it's an apparent shift. So when it's an apparent shift, that means I think it sounds different. I hear it differently. I'm like experiencing the ambulance moving past me differently, but it's not actually different. And the reason that happens is because the ambulance is moving. So even if I stand still, as that ambulance comes closer to me, the waves tend to bunch up, okay? When the waves bunch up, that means they have a higher frequency. That's why I have that higher pitch, the hurting of my ears. Once it moves away from me, though, now the waves can stretch back out because me, the observer, is further away from the actual ambulance. So I don't hear it as loud or as higher pitch, okay? So that makes sense how the waves can kind of scrunch together and then they can spread back out as they're moving away, okay? So that idea, we didn't get a chance to really talk much about the universe this year. Redshift, blue shift. If you take astronomy next year or the year after, they talk about redshift, blue shift. If the universe is contracting, other stars that are really far away would be coming closer to me, right? So if they're coming closer to me, those waves bunch up, higher frequency, right? So the light emitted from the stars would be shifted towards the blue frequencies. But if it's expanding, that means all those stars would be moving away from me. So as that ambulance moved away, remember they stretched out. Longer wavelengths, lower frequency was redshift, okay? So when they look at, so on all those distant stars, there's hydrogen gas, okay? Those hydrogen gases actually emit a certain wavelength. And so they can use technology in order to figure out, well, where are those emission spectrums? Are they in the middle? Are they towards the red side of the visible spectrum? Or are they towards the blue side? They are towards the red side, so this supports the idea that our universe is expanding and moving further apart, okay? So that is the Doppler effect. Does that feel okay? That one's okay? Yes? All right, so like I said, frequency and pitch, they go hand in hand. So a higher frequency, higher pitch, hopefully you recognized that yesterday when you were using your tuning forks. So higher frequency, higher pitch, lower frequency, lower pitch. Do you remember which ones were higher pitch, the shorter ones or the longer ones? Shorter, good. So I added that just in case, since we had it on the board yesterday for you. So the longer tuning forks were the ones with the lower frequency, lower pitch. Shorter tuning forks, higher frequency, higher pitch. Okay? Now, the last one, diffraction. So diffraction, right now I'm talking, right? Can people in the hallway hear me? Probably. Yeah, right? If I'm super loud, they can hear me down the hallway, right? So that's because as I'm talking, my sound is going throughout the room, that energy, the wave front's moving throughout, but then it has to pass through that door. That door is a gap. As it passes through that gap, it's going to spread out. So do you see how even though the sound I'm talking inside the classroom, it can actually spread down to the rest of the hallway, okay? That's why some of your really, really loud teachers, if they ever have their door open, you can hear them down the hallway before you're even standing in front of their door, right? So here, can you guys think of how we might use diffraction? Megaphones, right? So megaphone would be a really good example. So a cheerleader shouting through the megaphone, what's that going to do with the sound or the cheer? It's going to spread it out, right? So even though they're going to be shouting and they're going to be yelling into that actual opening, that allows for the sound to be spread out and to hit more of the actual stadium, right? Get more of the people energized, get them part of the game, things like that, okay? All right, so last 2 slides, we're almost there. So those key takeaways. Reflection is when it bounces back. Sonar, echoes, that would be reflection. Refraction is when that light bends because it goes in a different medium. So trying to reach for the actual animal at the bottom of the ocean or the diving ring, whatever it may possibly be, it looks like it's in one spot, but it's actually slightly off from that spot. Or the straw or the actual pencil in the cup of water, refraction. Diffraction, that's our megaphone. The sound spreads out more as it passes through a small opening or a small gap. Doppler effect, that's as it comes closer to us, higher frequency, higher pitch sounding. As it moves away from us, lower sound, not as high pitched, not as damaging to our ears. And then last one was that interference, which we talked about, those noise canceling headphones, in order to be able to take away any of that background noise that we might have. Okay? And then ultimate last final reminder from yesterday. Does amplitude affect the speed? Wavelength? Frequency? Only thing that affects it, how close the particles are together. The medium through which it travels, the temperature of that medium, things like that, okay? So one final reminder there for you, wave speed is only dependent upon the medium, not the properties of the wave. So not how tall it is, not the wavelength, not its frequency, okay?